So far, we have operated safely above threshold. Coherence exceeds the minimal stabilization requirement. Geometry exists. Curvature evolves. Propagation is invariant. Everything has been derived under the assumption that stabilization holds. Now, we ask, what happens when coherence approaches threshold from above? Because threshold is not merely a starting condition, it is a boundary. Below threshold, geometry does not exist. Above threshold, geometry emerges. So, what occurs near that boundary? To answer this, we return to stabilization. Stabilization requires coherence density to exceed a minimal value. If coherence density falls toward that value, structure weakens, metric robustness declines, curvature response becomes sensitive. Near threshold, small variations in coherence produce disproportionately large geometric effects. Why? Because curvature reflects gradients relative to stabilization scale. If coherence density is barely above threshold, gradients represent a large fraction of available structural support. In such regimes, geometry becomes fragile, curvature intensifies, propagation slows or distorts. Now consider gravitational collapse. In conventional theory, extreme curvature appears near massive compact objects. In this framework, extreme curvature corresponds to regions where coherence density concentrates sharply relative to threshold. As coherence density increases locally, redistribution pressure intensifies, curvature steepens. But redistribution is constrained by finite propagation. If coherence accumulates faster than redistribution can compensate, local stabilization stress rises. This produces structural compression. If compression continues, coherence may approach threshold boundaries elsewhere. And this is critical. Threshold proximity does not occur only from below. It can also occur indirectly. Extreme coherence concentration in one region may starve surrounding regions. Coherence must redistribute. If redistribution lags, neighboring regions may dip toward threshold. So collapse is not merely concentration, it is imbalance across structure. Now consider singularities. In classical relativity, singularities represent breakdown of geometric description. In this framework, singularity corresponds to threshold violation. Either coherence density becomes so extreme that metric structure loses smoothness, or coherence elsewhere falls below stabilization requirement. In both cases, geometry ceases to be a reliable encoding. Singularity is not infinite curvature in a literal sense. It is structural breakdown of stabilization. Now consider black holes. In conventional theory, black holes possess event horizons beyond which causal influence cannot escape. In our framework, extreme coherence concentration produces steep curvature gradients. Propagation remains finite. If coherence imbalance becomes large enough, redistribution pathways narrow. Regions may become effectively isolated by propagation constraints. This produces horizon-like behavior, not because spacetime tears, but because coherence redistribution cannot bridge the imbalance region. Now consider time dilation near such regimes. Earlier, Lorentz symmetry emerged from invariant propagation. If propagation becomes constrained by steep curvature gradients, the effective ordering of events slows relative to distant regions. Time dilation is not mysterious. It reflects redistribution stress. Regions under high coherence gradient experience slowed structural adjustment relative to regions of lower imbalance. Now consider early universe conditions. In extremely early stages, coherence distribution may have been near threshold across vast regions. Geometry would have been fragile. Small fluctuations could produce large curvature variations. Dimensional behavior may not have stabilized fully. Propagation symmetry may not yet have reached large-scale invariance. In such regimes, effective dimensionality could differ temporarily. As coherence density increased and stabilized, geometry solidified. Threshold was exceeded robustly. Spacetime emerged as stable large-scale encoding. This reframes cosmic origin, not as spacetime emerging from nothing, but as stabilization crossing threshold globally. Now consider extreme density collapse again. If coherence density rises sufficiently high, redistribution cannot smooth gradients instantly. But conservation still holds, so coherence must remain bounded. Infinite density is structurally forbidden. Instead, collapse must redirect into redistribution channels or dimensional restructuring. This suggests that classical singularities are artifacts of extrapolating geometric encoding beyond stabilization validity. Geometry fails first, not structure. Now consider observable implications. If threshold proximity produces fragile geometry, regions near extreme gravitational environments should exhibit deviations from classical prediction. Propagation speed invariance must hold, but effective curvature response could shift slightly. Metric robustness may vary subtly. This suggests that black hole interiors, early universe epochs, and ultra-high-density systems are testing grounds. Now pause. We must remain disciplined. We are not claiming resolution of singularities. We are not dismissing relativity. We are identifying where geometric encoding ceases to be valid because stabilization approaches threshold. This is a structural boundary, not a mathematical trick. Now consider dark energy-like behavior. If global coherence distribution drifts slightly relative to threshold over cosmic scale, large-scale curvature behavior could shift gradually. Expansion acceleration might reflect coherence redistribution across vast structure, but that belongs to later analysis. Today's conclusion is narrower. Threshold is not merely a starting condition, it is a boundary of geometric validity. Near threshold, curvature response amplifies. Propagation experiences stress. Geometry becomes fragile. Singularity-like behavior emerges. Horizon-like isolation appears. Beyond threshold violation, geometry ceases, but structure remains. This means extreme regimes are not failures of theory. They are boundary behaviors of stabilization. Now step back across the arc once more. Difference, refinement, stabilization, threshold, metric, curvature, dynamics, dimensional selection, Lorentz symmetry, extreme regimes. We have reached the structural edge. Only one major conceptual reinterpretation remains. In the next episode, we examine something controversial. If curvature reflects coherence distribution, then what we call dark matter may not require unseen mass. It may reflect misattributed coherence geometry. We proceed carefully, not as denial, as reinterpretation.